How's it going, everyone? Hope you had a good weekend. I got into some paint yesterday, so I'm still covered in paint. So if you see white stuff on my hands, that's what it is. All right, so y'all ready? 8.5. We're going to cover 8.5 today. We're going to do the whole thing. I don't think we need 2 days for it. And then we're going to get right into 8.6 next time. And then next week is our last 2 classes. So hopefully we can get through chapter 8. I feel good about it. Let's get down to business. So we're going to do a power series to start. I thought I had this open. Where is it? Here we go. All right, come here. Oh no. There y'all are. Okay, so power series. Make this bigger for you. All right, so where we are, okay, like what have we done up to this point? We've established all the different tests, all right? We feel good about some of them, others we're not too sure about, but we have a basis of test in place. And I told you the good news was that the ratio test was going to be the one that we're going to be really using a lot as we proceed. In fact, pretty much for everything we do from here on out, it's going to be ratio test. So that's good news, I think. So what we're going to do now is we're going to define a new type of series, all right? And I want you to pay close attention to the fact that our series is now going to contain a variable. Up to this point, our series have just been a bunch of numbers added up together, right? So, you know, 1 plus a half plus a third plus a fourth, something like that. But now we're going to have variables involved, actually just one variable. So let's define a power series to start. A power series is a series of this form. So you have sum n equals, look where it starts, n equals 0 to infinity, all right? And then we have c sub n, and then times x to the n. Now the c sub n in the formula, that is what we did last time. In other words, if we were to take the x to the n out, we were looking at series that look like this, n equals 1 to infinity of a sub n. And we always started at 1, but we're going to start at 0 because, you know, why not? I mean, we can start the index anywhere we want. Even though it kind of contradicts when we first started about talking about sequences, we always said, let's start at 1, right? Well, now we're just kind of very quickly going to be like, no, we can start at 0 if we want to. All right, we're just shifting the index. So we had n equals 1 to infinity, and then this was a formula, right? This was a formula for a sequence that created a list of numbers, and then we're just adding them all up. The c sub n here is basically what the a sub n used to be. It's just different notation, okay? When we do power series, we use c sub n instead of a sub n. I don't know why, but we do, all right? And then we have the very important x to the n. So those are just powers of x, right? Those are just powers of x. You start out, you'll have x to the 0, which is just 1, then x to the first power, then x squared, then x cubed, and thus the name power series. It is a series that is made up of powers of x, right? They're all, every term in the series is a power of x, and thus the name power series. And it is actually, if you think about what x to different powers is, this is basically a polynomial, right? It's a polynomial, kind of. It's an infinite polynomial, meaning that it goes on forever. When we studied polynomials in college algebra, like the highest power we ever went to was like 4, 5, 6, maybe 7. But we knew that when we learned them, the power could be as high as you want. But you would have to stop somewhere in college algebra. Here in Cal 2, we have an infinite polynomial, which is this thing called the power series. All right. And I'll kind of a spoiler here. And I think I've told you this before. Pretty much every function out there that you could ever come up with can be turned into an infinite polynomial. There's a theorem called the Wow Strauss Theorem that says that you give me a function, I can create an infinite polynomial as close to your function as you ever want me to be. All right, now that's for later, okay? All right, so what's different? I think I just pointed out that our power series, we don't know what x is, right? X is a variable here, right? X could be different values. And since we don't know that, we don't know the value of x, it's not given to us, we actually don't know whether or not we're going to get convergence or divergence for this series, because I can only determine convergence and divergence if I have a bunch of numbers added together, right? But if you throw in a variable, well, then I don't know, right? I don't know. So we have this series that may or may not converge. It all depends on x, right? You get the idea? Now, if it converges, it goes to a number, right? We said that already. We don't necessarily know what number it goes to, but it will go to a number if it converges. And if it diverges, well, then it goes to like infinity, or perhaps it just doesn't converge, right? It just doesn't go to a number. So start think about this abstractly. We have this new thing we're calling a power series. It depends on x, right? And some x's will make it actually make sense. Like some x's we plug in and we get a number. Some x's we plug in and we don't get a number, like we don't get anything. Does that sound like something you've dealt with in the past? Things where you plug numbers in, sometimes it spits a number out, sometimes it can't handle the number. That's a function, right? That's what a function is. So we are going to now kind of think about a power series as a function. A power series can be viewed as a function. We define f as follows. So we're going to define some function f of x to be this power series, which depends on x, right? So the value of the function depends on x. The function only makes sense if it converges. Like it would make absolutely no sense if it didn't converge. The illustration here to compare it to is if I define the function f of x equals square root of x, there are certain numbers I can plug in, certain numbers I can't plug in. When I plug in 4, I get 2, right? I plug in -4, I get undefined. Well, we're not doing imaginary numbers here, right? So that's exactly what this is. We have a series, a power series, where when we plug in certain x's, we get a number, and when we plug in other x's, well, it doesn't make any sense. So again, I'm just drilling this in here. It's only defined if we plug in certain values of x that make the series converge. Therefore, it has a domain, all right? This function will have a domain. And the domain of that power series function are the values of x which make it converge, all right? Is this all kind of making sense abstractly? Any questions up to this point? Okay. So let's look at a first important example, all right? Because it's always great to start with examples. All right, so let's define a power series, all right? Now, sorry, I'm going to go back up here. All power series have to look like this, right? All power series have to look like this. So the only thing that, and this is a very important but subtle point, the only thing that differentiates one power series from another is this. All power series have to have this in it, x to the n. It's the numbers in front of the x to the n's that are going to differentiate one power series from another, all right? So this formula is vital for us to be able to distinguish one from another. And this is kind of a crazy idea because it's saying that the only difference between two functions, remember I said if I give me two functions, I can give you power series for both. Sine of x has a power series. Cosine of x has a power series. They both have their own power series, and they're different from one another. And what differentiates the two from one another is the numbers in front of the x's. They both would have x to the 0, x to the 1, x squared, x cubed, x to the 4th. They'd all have those. It's the numbers in front that make the difference. Okay, so I'm going to give you your first example, and this is the easiest example of any power series you could have, and that is the power series where I'm going to define that c sub n in front to always be the number 1, right? So all power series look like this. And I'm going to say, you know what, this formula here, I'm going to make it real simple for you. It's not even going to be a formula. It's just going to be a constant. Let's just replace it with 1. All right. So if we do that, then all we're going to get is, well, first plug in 0, x to the 0 is 1, so you get 1. Then x to the 1st, right, with a 1 in front of it, then x squared, then x cubed, then x to the 4th, so on and so on, so on and so forth forever, right? This goes forever and ever. So what we'd like to know is, what is the domain of this function? For what values of x will this converge? For what values of x will this diverge? So let me give you just a mental exercise. What if I asked you to replace x with 1 right now? Plug in 1 to this function. Wouldn't this just be 1 plus 1 plus 1 plus 1 plus 1 forever? And wouldn't that diverge? Because if you add up ones forever, that's infinite, right? So if I plug in 1, it should diverge. If I plug in 2, it should also diverge, shouldn't it? Because it'll be 1 plus 2 plus 4 plus 8 plus 16. That should get huge, right? But what about something like 1/2? What if I plugged in 1/2?
That'd converge.
Okay, why would that converge if I did 1/2?
Because each thing being added on is significantly smaller by a really large margin. And we've already dealt with this effective situation before of a fraction that's getting smaller and smaller and smaller being added. And almost every time we had that, with some very rare exceptions, they were converging to some weird little fraction between like 1/2 and 1.
Okay, good. I'm going to challenge you a little bit on that to think about this. So we have seen that when we add up things where these get smaller and smaller and smaller, that sometimes it converges and sometimes it diverges, right? Harmonic wouldn't, right? A harmonic would definitely diverge, right? But you said that we've dealt with this before, this specifically. Do you recognize this? Do y'all recognize what type of series this is?
That's something to do with P series?
Let me write it out. This is some, and I'm going to write it starting with 0 to infinity. This is 1/2 to the nth power. Do y'all agree? You have a fraction
Geometric?
to the n. It's
Yeah,
geometric. It's geometric. Remember, P series, the thing that changes is the base, and the power is fixed. Always remember P series. P is power, and the power is fixed.
But
Okay.
2 over 1 is still 1, and the power is changing on the bottom. But if the consistent power. Oh, sorry about that.
Yeah, it's with a P series, it's always the same power. So like a P series would look like this: 1 over 2 to the 3rd plus 1 over 3 to the 3rd plus 1 over 4 to the 3rd plus 1 over 5 to the 3rd. That would be a P series, because it would be, well, let me start off with 1 over 1 to the 3rd. This would be 1 over n to the 3rd. That's a P series. Understand? See the difference between the two? And this would converge because P is bigger than 1. Just side note there. So this is geometric. Do y'all see that? This is geometric. Okay, I'm gonna talk about this in the notes right now. So let's continue. All right, notice that this looks just like our standard geometric series, right? Go back up here, compare this to this. What do we have? The only differences we have here is that the A is 1. Oh, and also remember on geometric, when I was showing you all geometric, I told you that it is possible to have n start at 0 and the formula looks a little different, right? So that I'm using the second version of the formula for geometric that I gave you. there were two versions, right? The first version was this one. That was the first version of a geometric series. Now we're kind of saying, remember the second version? If we look at the second version, if I tell you to replace A with 1, and if I tell you instead of using R, use the letter X, then this is exactly a geometric series, isn't it? With A being 1 and R getting replaced with X. And so we know exactly what would happen with the geometric series, don't we? We know. It converges if what? Geometric series only converge if what?
They're less than 1.
If what's less than 1?
The R is less than 1.
Absolute value of R, right? So if the absolute value of R is less than 1, it converges, which means for us, this should converge so long as I use something, as long as I plug in an X that is less than or equal to 1. I'm sorry, yeah, an X where the absolute value is less than or equal to 1. I say that right here as well. We know this will converge if the absolute value of R is less than 1, but in our case, since we're using X instead of R, we need the absolute value of X equal to 1, or less than or equal to 1. Therefore, the domain of this function, right, the domain of this, the only values of X that you could actually plug in that would make any sense is values between -1 and 1, not including the endpoints. Okay. So I'm going to write this on the side because this is really kind of like the big conclusion of this example. So what we're saying is if X lives between -1 and 1, okay, then the sum n equals 0 to infinity of X to the n, which is the same as 1 plus X squared plus X cubed forever, right? This will equal 1 over 1 minus X. Now, where is this coming from 1 over 1 minus X? What is that? Where am I getting that from? What is
From testing the convergence.
That's remember what a geometric series added up to be? A geometric series, if it converged to A over 1 minus R, right? But for us, A is 1, right? And R is X. Y'all got that? So A is 1, R is X. Look, I can't overstate what this statement is saying to us, all right? Because this is where you really have to make the connection. So what I'm going to do is go to Desmos, all right? Let's see if I can get Desmos in here. Okay. I'm going to leave that on the thing because I want to 1 divided by 1 minus X. Okay, that is the graph. That is the graph of 1 over 1 minus X. All right, everyone? This is the graph of 1 over 1 minus X. What I'm telling you is that instead of graphing that function 1 over 1 minus X, you could graph this infinite polynomial 1 plus X squared plus X cubed forever, and they would be the same graph, the exact same graph, but only between -1 and 1. So if we just look between here and here throughout the rest of this, the infinite polynomial is equivalent to the 1 over 1 minus X. They would look exactly the same. Now, I have a better animation for you. This was just to get you thinking, all right? So within my notes, I have an interactive thing. So here I need to go a little smaller with this. Here again, I have the graph of 1 over 1 minus X. Everyone see it? And I am highlighting just between -1 and 1, that's the white region. And then to the left of -1, to the right of 1, it's grayed out. I want you to kind of ignore those areas. And what I'm going to do is start graphing the infinite polynomial. Now, I can't graph an infinite polynomial because it goes forever, right? So I'm going to start doing it piece by piece. So the infinite polynomial was 1 plus X squared plus X cubed plus ... right? Let's start by just taking the first term. If I were to ignore all of these and graph one, that would be a constant one function, wouldn't it? Just a flat line, and that's this black line. You see the black line? That's one. Do you all agree that the red function and the black function don't look at all like they're the same thing, right? Okay, let me graph 1 plus x. Here we go. 1 plus x. So do you see here in black, it says 1 plus x? That's what I'm graphing. 1 plus x is better, but it still sucks, right? It's a line, all right? So now I'm going to do 1 plus x squared, which is going to be a parabola. It's better. Notice I'm leaving a dotted line behind. So when I go to the next stage of the series, I'm leaving the dotted lines behind so you can see what it was before and now what it's turned into. That's better, isn't it? Let's do the next term, 1 plus x squared plus x cubed. Okay, better, a little bit. Let's keep going. Notice what's happening over here. Notice what's happening here and notice what's happening here. Here we go again. Do you see it like marching its way towards that graph? Now I have to stop at some point, but okay, I'm starting to make my computer think too much. I've gotten pretty damn good, haven't I? Would you agree that the black and red functions are pretty close to one another right now? Only between -1 and 1 though. Once you get outside of -1, do you see that they're not even close to one another? Do you see like they're not even close, but that I never expected them to be. It was only between -1 and 1 that I expect these two things to be equivalent. So this is interesting. Is it useful? I don't think we can understand why this is useful yet, but it's definitely interesting that there's a way to represent a function, right, with a power series, and that within some region, some window, they're the same thing, as long as, you know, I go out far enough. I have to go far enough though. So the things that you might be thinking right now is, well, what's useful about this? 1/1 minus x is not that bad of a function. So why don't we just deal with that? Why mess with its power series, right? Like if you asked me to integrate that or differentiate that 1/1 minus x, I'd have no problem doing derivatives or integrals of that, right? But the thing is this is a simple function. What if I give you a very complicated function? Wouldn't it be very nice if we could come up with its power series? If we could, then how would the differentiation work? If I asked you to take the derivative of this right here, you would probably be very happy to do that for me, right? Derivative of 1 is 0, derivative of x is 1, that's 2x, 3x squared, 4x cubed, 5x to the 4th, right? It'd be so easy to take derivative of this because you can just do derivative of powers, which is like the very first rule you learn in Cal 1. It's super easy. Now, the question
the integral wouldn't be too much harder either.
Yeah, the integral would be the exact same thing backwards, right? X, 1/2 x squared, 1/3 x cubed, 1/4 x to the 4th. So integrating and differentiating this will be super easy. The question would be, how do we get from the complicated function to the power series, right? How do we get from the complicated function to the power series? Well, that's 8.7 in this chapter 8, section 7. All right, so we're going to get there, but we need to have some understanding of power series first. All right, so I told y'all when we were doing techniques of integration by parts, partial fraction decomposition, trigonometric substitution, all those different things, I was saying in the real world, you probably can't integrate by hand the functions that you would ever run into. So you're probably going to use a computer to integrate a function, and the computer is going to use the series. It's going to use the power series and then integrate and differentiate that way. So, or if you had to do it by hand, we would want to convert the function to its power series and then differentiate and integrate. And converting from a function from a crappy function to its series actually turns out to be not terrible because we have a very, very elegant formula. All right. Let me back my computer up so it's not trying to do this in the background. Okay. That's pretty cool, right? Another thing I want to mention right now is you might be like, well, you know what? This isn't very useful also because I'm only in a window, right? I have to be between -1 and 1. What if I was interested in this function and what it was doing like over here near 2 or 3, right? Not what's happening between -1 and 1. Well, there is a way that we can shift this over where the window becomes in the region we want to play in. All right, and that'll be again later on, we're going to be able to shift. All right, so if you're concerned about the window restriction, we've got a workaround for that as well. So, all right, let's keep going. All right, so I kind of lied to you a little bit when I gave you the first definition of a power series, right? This was it right here. And I told you every one of them is going to have x to the n. I lied a little bit. Okay, so I'm going to give you the general definition of a power series now, which is one slight modification. Pay attention to the formula here. Okay, the only difference is instead of doing x to the n, I'm going to do x minus a. Now think back to college algebra. When you subtract a number inside of a function, what does that do to it visually? When you subtract or add a number in the function. Lewis is pointing, it moves it left or right, correct? Doesn't subtracting a number inside the function moves it to the right. Adding a number inside the function moves it to the left. It's opposite of what you think, right? So all I've done here is exactly what I just said a second ago, which was that window, we're going to be able to move it. All we have to do is kind of think about a general left and right shift of the series, which gives us our most general formula. Now, this is what's called, I've heard it called 3 different things. A power series about A, which just means you've moved it, right? You've moved it by A. It's also called a power series centered at A. Or you could it could be called a power series in x minus a. I don't make these things up. Okay, this is the language that was given to me, and I'm just giving it to you. Other than that, everything else stays the same. Okay, everything else stays the same. You still have numbers in front that keep changing, and then the powers on the x minus a keep getting bigger and bigger and bigger. Notice 3 things about this. First thing, this is the same formula that I just told you, right? So back up here, when I give you this first definition, right up here, when I gave you that first definition, what I was really lying to you about was this. This right here was really x minus a to the n, but I was letting a be equal to 0, right? That's what I was doing. I was saying let a be 0. And then if a is 0, it's x minus 0 to the n, and then that means just x to the n. So could we not say then that this right here is a power series about what?
0.
0. Or you could say power series centered at 0, right? Or you could say a power series, what was the last one? At
Professor, at a equals 0.
What's that?
At a equals 0.
I'm using the language here. Let me scroll down. Okay, a power series about 0. A power series, yeah, so a is 0, right? We don't necessarily need to state a is 0. We're just going to replace a with 0.
Okay. I have a question. So
Yes.
when you move your bounds between a certain amount, can you move them in infinitesimally small amount and they will still work? Like let's say 0.0001. Like let's say we're looking at an atom, right? And then we're trying to find the power series of the series to like an atom that moves or whatever. can we go like infinitesimally small where a equals to 0.001 or something extremely tiny? Will the polynomial still work well, or?
Yeah, yeah, absolutely. You can shift this function however much you want. Now, when you shift it, it may or may not converge. It just depends. Like, you know, the power series are only valid. Well, we're getting ahead of ourselves. We are getting ahead of it. Stay tuned. At the very end of this, I'm going to give you power series are going to wind up having 3 different things that could happen when it comes to convergence on where they converge. All right. So just stay tuned. But as long as it has some region where it works, the power series is good, we can be shifting by infinitesimally small or by a lot. A is any number we want, any real number. All right. So first thing, this thing right here, this general formula, we already looked at it with a is 0 to start. Also, this x minus a to the 0, that term right there, we are going to define this. God damn it, come on. We are going to define this to be 1. We are defining this to be 1. Now, you might be saying, why define that to be 1? What the hell do you mean? Anything to the 0 is 1, right? Take any number, raise it to the 0, you should get 1. But the reason I have to define this to be 1 is because what if I tell you to plug in for x, what if I tell you to plug in a? What would happen? What's a minus a? 0. And then 0 to the 0 is not 1. All right. So we are defining that first term. This one right here will always be 1, regardless of what x is. Because if x is a, that's going to cause a problem, right? Now, if x equals a, right? If x equals a, then all of these guys, which I'll do in a different color, all of these guys would be zeros, wouldn't they? If x was a. So if x is equal to a, then every single one of these would be zeros. So long as my n is bigger than or equal to 1. See, I'm not looking at that first one because that's going to cause an issue unless I define that to be 1. It's kind of like, you know how I told you 0 factorial is 1, and we did talk a little bit about why it's 1, but we defined it this way. That's what I'm telling you to do here. We're defining x minus a to the 0 to be 1 when x is a. All right, so the whole point is this. If I give you a power series and I tell you to plug a in, okay? If I tell you to plug a into any power series that's centered at a, you should get convergence. Let me say that again. If I give you a power series centered at a, that's what it must look like. Then if I tell you to plug in a into this, right? Plug in a, then all of these guys go away. And the only thing you're left with is c sub 0. So this would be c sub 0 if x equals a. And c sub 0 is a constant, which means you have convergence. It converges to the number c sub 0. For any power series, right? Any power series, as long as if I plug in where it's centered into it, I'm going to get convergence, which means that every power series that you could ever deal with in your life converges for at least one value. It may not converge anywhere else, but it converges for at least one value. Go back up to the example we just did right here. This one right here, the geometric series.
I have a really quick question. So when you miss your bounds between, like, let's say, never mind. I don't know. I don't know how this makes sense, but let's say you have insert value of 3 into your power series, and you already shifted your function to a, and let's say a is 3, then that will only be equal to that number, which is c sub 0.
Yes,
Is that what you're saying?
that's exactly right. If
Oh,
you have a power series, and let's say you've shifted it 3 units to the right, so you let A be 3, and then you say, hey, plug 3 into this, it will converge. That will converge to C sub 0. Now, we're getting somewhere with this. We're getting somewhere with this. I just want to make sure you understand that every power series converges at least one point. Look at this example right here. What did we say A was here? What's A here?
0.
A is 0, right? This is centered at 0. So that means if I plug 0 in for X, I should get convergence. Does it? Well, replace all your X's with 0. What do you get? You get 1. That's a number, right? That converges. Every power series does that. If I gave you this power series, I'm just going to make one up, okay? Sum n equals 0 to infinity of n plus 1 over n factorial times x minus 7 to the n. That is a power series. You've never seen a power series like that before, but that is a power series. This right here is our c sub n. This right here is our x minus a to the n, all right? So we are trying to look at this as being a function. And so if I ask you, hey, what's the domain of that function? You have to figure out for what values of x will this converge, for what values of x will this diverge. What you can tell me right now is that it converges for at least one value. What value is that?
X equals 7.
7, right? 7. We know that this will converge at 7. The question is, does it converge at 7.1? Does it converge at 10? Does it converge if you try and plug in, you know, any other numbers, right? But every power series converges at least one point. All right, let's keep going. Our first example where we're going to actually have to think about it, right? So here's our first example. I'm going to take a screenshot of this and we're going to go work this out. Hey, wait a minute. Hold on. I thought I had done this already. Okay. All right, if f of x equals sum n equals 0 to infinity of n factorial x to the nth power. First of all, the question is, what is a?
0.
0, right? Because it's just x to the n. All right, so a is 0. Any questions there? A is 0. All right. So that means we know if we plug 0 into this, it converges, right? If we plug in 0, it converges, but we don't really know anything else. All right, B. All right, what is the formula for C sub n?
It's in
So
factorial.
It's just the n factorial sitting in front. Good, right? With me? Part C, what is the domain? All right, so here's what we're saying. If I'm asking you for the domain of this function, and this function is a power series, then I'm asking you to figure out what makes this converge, right? What will make this converge? Well, I'm going to have to figure that out. I'm going to have to figure out what x's make it converge. So I go to our previous section. I say, well, how do I figure out whether or not a series converges or diverges? Let me try the ratio test. Let me try the ratio test. I'm going to do a ratio test on this. And the ratio test says this. I want to take the absolute value. Now, you know what? Let me write the ratio test up here. I'll do it on the bottom. The ratio test said this. If you're given a series, right, a sub n, then if the absolute value of a sub n plus 1 over a sub n, if that's less than 1, then we get convergence, right? That's what the ratio test said. And so this A sub n in here was the formula inside the series, right? That's what it was. For us, the A sub n is all of this. This is what the A sub n is for us, if we're going to use the ratio test, which means I need to first plug n plus 1 into this.
So
So
A sub n is G sub n?
No, A sub n is not C sub n. A sub n is the entire formula. Because the ratio test says, hey, if you have a series, take all the crap that's in the series, evaluate it n plus 1, and then divide it by that series evaluated at n, look at that absolute value of that ratio and hope it's less than 1. For us, this is the whole thing that we're evaluating. Now, in terms of a power series, we call this thing C sub n, and then this right here is the x minus a to the n.
So after the ratio test, X will converge or diverge, or we isolate X and then
We have to figure out what, let it play through. Let it play through. Let's work this out. Trust me, when we work it out, you'll see it. Okay, you'll see what's going to end up at the end is going to be some
sorry about
statement
that, my bad.
No, it's okay. It's just you're thinking ahead, which is good, but it's hard to explain it until we work it out. And there's different scenarios we're going to run into. So there's actually 3 scenarios that we're going to see. So let's do this. Let's first plug in n plus 1. So I do n plus 1 factorial, and then x to the n plus 1. Right? That's basically me plugging n plus 1 in the whole thing. And then I divide that by just this at n, which is this. And we want this to be less than 1, right? We want this to happen. We want that absolute value to be less than 1, because that would give us convergence, wouldn't it? Yes, yes, yeah. Okay, so let me move this down. This was separate idea here. This was me just explaining what the ratio test is from last time. Okay, let's simplify this. This is the same as, let's see, we can do n plus 1 factorial, we can write as n plus 1 times n factorial. We've done that several times now. I said it's a very important property of n plus 1 factorial. And then this can be, the x to the n plus 1 can be written as x to the n times x. Again, that's just properties of exponents. We've done that. N factorial or x to
Plus
the n.
1. That's 1.
Plus, yeah, thank you. To the 1 is what I meant to put, sorry. Now cancel n factorial, x to the n. Right? Oh, you know what I'm missing? Shit, I'm so sorry. Ooh, gosh, I'm fired. Limit n goes to infinity. We're supposed to take this limit. Sorry, the ratio test has a limit in front. Sorry. Limit n goes to infinity. Must be Monday. All right, so I'm going to take the limit as n goes to infinity of n plus 1 times x. I want that absolute value to be less than 1, right? I want this to be true. I want that. Please, let's let that happen. Okay. Pause. When you have a function back in college algebra, you can plug a value into it, right? You can plug a number into it, but you can't plug infinity into a function, can you? If I give you the square root of x and I say, hey, what's plug in infinity, you can't. You could plug in a billion, fine. But the x is a fixed number, right? X is a fixed number. So when you look at this, right, I want you to be thinking about that x right now. It's going to be a fixed number, all right? And n is going to go to infinity now. So what happens here? This goes to infinity, right? Times some fixed number. And I need the absolute value of that to be less than 1. That's not happening. There's no way I can keep this thing less than 1, right? If I fix the x, I can't do this unless x is one value and one value only. What value? 0, right? 0. But we already knew 0 would work. How did we know 0 was going to work? Well, because A was 0, right? And what I just said prior to this was that every power series converges at least one point. And for this, because it's centered at 0, it should converge if we plug 0 in. And that's exactly what this is telling me, is that the only way, okay, the only way this works, or this holds, I should say, is if x is equal to 0. Otherwise, it's bigger than 1, right? Which means there's only one place it converges. Therefore, the domain of this function is a single number. That's it. We know how to write intervals, right? Like if the domain was everything between -1 and 1, we know how to write that, right? But how do you write a domain when it's just a single number? We call these singletons. What you do is you write the number in a set of curly brackets or braces. You go 0 like that. That's the domain. I promise you, you've never had a function like this ever in your life before. It's a shitty function, okay? Because you can only plug one number into it, right? The only number you can ever plug into it is 0, and it spits out 0.
Wait, I'm confused. Is that what is that works within the function that we're comparing it to? For example, the power series that it's comparing it to, or
Nope. Nope. I'm saying this power series is a function which has a domain that is only the numbers for x, the values of x that will make this thing converge. And what we just determined was that there is only one value that makes this converge, and that is the value 0.
so I can't.
If I were to graph this function, here's what this function looks like, okay? And I literally mean this, right? If I ask you to graph the square root of x, everyone knows how to graph the square root of x, right? Yes, but I'm asking you to graph not that function. I want to graph this function, f of x equals sum n equals 0 to infinity of n factorial x to the n. I'd like for you to graph that function. What we just determined is that this graph is only defined at one point. It's only defined if you plug in 0. So if I plug in 0, it spits out 0. And so there's the graph of the function. Not a very useful function. But the illustration, the thing I wanted you to see in this example is that it is possible to have a power series defined in such a way that it only converges at a single point. They're not very useful, but it's possible that you only have one point in the domain. Lewis, now did that answer your?
Absolutely not. Okay, so you're telling me that a function of anything to equal just 0, like I haven't seen that, like ever.
This
But you're
particular
telling me
function.
that this particular function
Mm-hmm.
is going to only give me the result of 0 if I plug in 0.
That's right. If you try and plug anything else in, it won't work. So like, for example, what would happen if I tried to do, what if I tried,
One, just one.
let's go with 2. Let's go with 2. I think 2 will be more interesting to look at. So here is the function, right? We define this function f of x to be equal to this, n factorial x to the n. Okay, so what is f of 2? F of 2 is sum n equals 0 to infinity of n factorial 2 to the n, right? Let's start plugging in values of n. This is 0 factorial 2 to the 0 plus 1 factorial 2 to the first plus 2 factorial, 2 factorial 2 squared, yeah. And then 3 factorial 2 to the third. Understand? I'm just replacing n with 0, then with 1, then with 2, then 3. And then I keep doing this forever. This is going to go to infinity. I mean, you can see the numbers are getting huge, right? The only number you could ever do would be 0, and it would work. It would get convergence.
So
If you
all
try,
series,
what's that?
so all series that that diverge only have 1 point.
I didn't say that.
Okay.
No, I said that this series only converges at 1 point. That's what I've said. This is just a first example, right? This particular one does this. Let's go investigate another one. I won't show this. Okay, let's go look at another one. Oh, you want to see it? Nah. Okay, all right, so how about this one? Same 3 questions for a completely different power series. Okay, what's A in the formula? 3, right? This is a power series centered at 3. So A is 3. Hey, right now, could you tell me right now, is f of 3 going to give me a number or not? If I try and plug 3 in this number, am I going to get a number? Is it going to spit out a number?
Should get a 0. You'll get a 0 right there, which get you 1 for your total convergence.
I should get something, right? I should get a number. It should not be divergent. This again goes back to the whole point. Every power series should converge at A. In the previous example, that was the only place it converged, right? Was at A. A was 0 in the previous example. That was the only place it converged. This one, yeah, we know it's going to converge at 3, but is that the only place? We're about to find out. What's the formula for B sub n here? I'm sorry, for C sub n.
1 over n.
1 over n. So good. We have to realize that this can be rewritten as 1 over n times x minus 3 to the n. If you pull that 1 over n out front, that's your C sub n formula. Questions on that? Sure. Okay, part C, I'm going to use the ratio test. Right? And what we want, right? We want the limit, sorry, I'd forgotten that last time, limit as n goes to infinity of the absolute value. Okay, I'm going to take the formula in here and I replace all n's with n plus 1. So I take x minus 3 to the n plus 1 over n plus 1, and then divide that by the formula with just n's instead of n plus 1s. And I want that to be less than 1. This is the same as the limit as n goes to infinity of the absolute value. Now I'm gonna, if you did your homework, you'll follow what I'm about to do right here. I want that to be true. So all I did there is I rewrote x minus 3 to the n plus 1 as x minus 3 to the n times x minus 3 to the 1. And then over n plus 1. And then on the bottom, I did a fraction. I flipped it and brought it up. And then we get some good cancellation there. Those go away. Right? So now here's where I am. I have the limit as n goes to infinity of the absolute value. Now, the way that I like to do this is I like the next piece that I write is going to be everything that has n in it. So I have an n on top. That was this n. And I had this n plus 1. I'm going to put that below it. And then I'm going to multiply that times the stuff that has x in it, which is just the x minus 3 in parentheses. Right? That's this piece. And then I need the absolute value of that to be less than 1. right? We want that to be true. Now let's let n go to infinity. If n goes to infinity, n is only impacting this piece, right? That's the only piece that n is actually impacting. And that goes to infinity over infinity. And L'Hopital one time on that would give us 1/1, wouldn't it? So we know that that piece goes to 1 when we take the limit. So this is going to the absolute value of x minus 3 less than 1, right? Because this turns into 1 in the limit. We want this to be true, right? That's what we want. We want this. We want that to be true. So now we need to kind of like just kind of pump the brakes here for a minute. Make sure everyone here knows how to solve an absolute value inequality like this. And this is a college algebra thing you may or may not know how to do. So I'm just going to show it to you. All right. If you've never seen this before, it's pretty easy to do. Okay. Whenever you have an absolute value like that, less than a number or less than or equal to a number, all you do is you write down the thing in the absolute value. You make it less than 1. So you basically have dropped the absolute value. But then on the other side, you do greater than, and then you do the opposite of this number, -1, like that. That's the way that you basically remove an absolute value from an inequality. You remove it, rewrite the inequality, and on the other side, you make it greater than the opposite of the number that was here. Y'all okay with this? Now I'm just going to add 3 everywhere. And so what I get is 2 less than x less than 4. So far, the domain of f is everything between 2 and 4. In other words, if you give me an x value between 2 and 4, then I know that this power series will converge. Why? Because if you give me a value of x between 2 and 4, then I know that when I run the ratio test on that, I'm going to get this to be less than 1, right? Right? It'll be less than 1. And therefore, I'll get convergence. I'm not telling you what it converges to. I just know that it will converge, which means these numbers are in the domain of the function. Does that make sense? Now, we have a complication that we need to address here. And this always costs students points on, lots of points on the final. So far, I have kind of found the domain. Remember with the ratio test, if this was less than 1, we had convergence. If it was bigger than 1, we had divergence, right? But what if it was equal to 1? Do you remember?
It's inconclusive.
It's inconclusive. The test fails. So right now, all we know is that if x is less than 4 or bigger than 2, we've got convergence. What we don't know is what happens at 4 and 2. Like, because think about this. What if I plugged in 4 right here? 4 minus 3 would be 1. The absolute value of 1 would equal 1, wouldn't it? It would equal 1, and that would be an inconclusive test. Or if I plugged in 2, I go 2 minus 3, that's -1, but then take the absolute value, that would be 1, and that's equal 1. So it's kind of like we've got this narrowed down to everything between 2 and 4. We just don't know what's happening at the endpoints. If we go past the endpoints, we know it's going to diverge because it'll be bigger than 1, but it's at the endpoints we're not sure of. So far this. Was there a question? But don't know what happens at the endpoints. Right? I don't know what happens at the endpoints. I'm talking about at x equals 2 and x equals 4. Not sure what happens, right? Not sure what happens. So check this out. All we're going to do is we're going to check. We're going to see what happens if I try and plug in 4. We're going to see what happens if I try and plug in 2. All right. So first, let me check. I'm going to go to a new page. So I'm going to now test, or I'm going to check, however you want to write. I'm going to test. Let's start with x equals 4. Now let me go grab the series. I would like to know what happens to this series if I let x be 4. So the series will look like this: sum n equals 0 to infinity, right? You know what, everyone? I just realized I have a typo here. That has to be a 1 on the series. Y'all see that? That has to be a 1, or else we had division by 0 to start. I need to go change that in my notes. Jeez, Robert. Let me do that now. See, I changed it here. Do y'all see I have it correct here? I apologize. Where am I? Here. Okay, so n equals 1 to infinity of, what are we doing? We're replacing x with 4. So what's 4 minus 3? 1. 1 to the n. 1 to
Yeah.
n power?
1.
1. So this can be 1 over n. Hey, does that look familiar? Does that look familiar? What is that?
Yeah,
A
it's
harmonic
P-series.
series.
It's harmonic series. It's harmonic, fixed over linear, right? This is harmonic. And therefore it diverges. Which means, do I want to include x or do I not want to include x? I do not want x in my answer here. Because plugging x into this function is like basically turning it into this harmonic, which diverges. Let's test the other endpoint. Test x equals 2. Now, if I plug in 2 into that series, something different happens. Do y'all see what happens if I plug in 2? 2 take away 3 is -1. That doesn't go away. -1 to the n over n. What's that? It's not harmonic. Harmonics don't alternate. Harmonic series linear over constant without any alternating. So how could you determine if this converges or diverges? What would you do?
AST.
You do the alternating series test. Good. So let's do an alternating series test real quick. The alternating series test, what we do is we have to show 2 things, right? The first thing we have to do is show that a sub n is greater than a sub n plus.
Quick
Yeah.
question here. An alternating series test. If it's like clear that n plus 1 is bigger than the other one, do we have to like fully go down and isolate for n, or do you want us to just, or is it okay just to be like, I don't know how to explain it. Am I explaining this correctly?
I think I know what you're saying. You're saying if it's obvious, right, that they're getting smaller and smaller and smaller, do you have to show it? Right? No? Is that not what you're saying?
Yeah, yes and no. I mean, sometimes it's not obvious, but we can just look at the base and be like, this thing is clearly getting bigger. This base is clearly bigger than the other base. It's going to divide by a bigger margin, which therefore subtract it.
I want to see it for this reason. In the alternating series test, you look at an alternating series and you have to identify what b sub n is. So what's B sub n in our series right here? What's the B sub n?
So
What's the
1 over
part-
n.
Yeah, good. It's the part that's not alternating. So it's just the 1 over n. So for this, B sub n is 1 over n. That's part of why I want you to show this to me, because I want you to be able to like extract the part of the series that's not alternating, and then show this is true. So let's show this is true. Is 1 over n bigger than 1 over n plus 1? This is a question, right? Clear the fractions. That's obvious, I think. N plus 1 is bigger than n. But if you subtract n on both sides, you get 1 is bigger than 0, which is true. So it's a decreasing sequence. And then the last thing I have to do is take the limit as n goes to infinity of 1 over n, and that goes to 0, which is what we had to show. Oh, sorry, I forgot to put that. We wanted to show these two things. Okay, so alternating series test says you have to show two things. You have to show it's a decreasing sequence, which I did, and you have to show that the limit as n goes to infinity of that B sub n formula in here, that goes to 0, and that does go to 0. So the alternating series test then tells me that this series converges, right? Which means we do want to include 2, right? Because 2 gets us convergence. So now we can finally answer part C. The domain of the function f is the closed 2 interval open on 4. In other words, this is all x's less bigger than or equal to 2, but strictly less than 4. You can write that either way. If you plug 2 into this power series, it's going to spit out a number. If you plug in anything past 2 all the way up to 4, it's going to spit out numbers. But if you try and plug 4 in, it's not going to work, and so it's not in the domain. This is I love these problems. Okay, this is a warning to you, or I guess a hint, not a warning. I like these problems because first, in the very beginning of the problem, you have to run a ratio test, right? So you got to get all this correct. And then once you get this interval, you have to realize, you know what, I have to check the endpoints. And when you check the endpoints, you actually have to run two tests. And each test you run is going to have a different type of series in it. And so you've got to be able to go back to the previous sections and figure out what those series are. In this case, it was harmonic and then alternating. So I ran 2 tests. See, I can give you a problem like this and like kill like 3 birds with 1 stone, right? Because you're not only doing the bigger picture of convergence, but the 2 endpoints require that you understand 2 specific types of series. All right, now, what is all this? Let's go and look at this function. I'm going to graph the function for you, okay? Remember, this function only makes sense between 2 and 4. So I'm going to show you what this function looks like. That's it right there. It looks like this black curve, but only look between 2 and 4. All right. So the first example I gave you, we looked for the domain, and we only had a domain at a single point, right? In the second example I gave you, I asked you for the domain, and we actually got an interval. So it was good. We actually had some function somewhere, right? We had a picture of a graph of a function. Now at one endpoint it was closed and the other endpoint it was open, but we had an interval of some sort. Single point in first example, interval in the second example. Third example. This is an example of what's called a Bessel function. Bessel functions are used in harmonics to model waveforms on, like, if you were to take a drum, right? If you were to take a drum, like, you know, a band, you play the guitar and the singer and the drummer, right? Take a drum and you hit it, right? What does the vibration of that membrane on the drum look like? Okay, when you hit it, what does it look like? That motion of that drum surface can be modeled with the Bessel function. Now, it's more complicated than that because this is this right here would be two-dimensional because it's like a regular function, but on a drum surface, it would be three-dimensional. But there is a Bessel function for three-dimensional as well. So let's just look it up real quick. Bessel function. Yeah, let's just do that and see what kind of images we can get here. So there's two-dimensional. These are what the two-dimensional Bessel functions look like. I was looking for the three. Oh, here we go. There we go. That's like vibrations on a surface. So vibrations on the surface of a membrane can be modeled with the power series, but a particular one. They're called Bessel functions. And it's important to note that there's no other function that you can use. Remember the very first example I gave you where we had 1 over 1 minus x, right? That was the very first example, 1 over 1 minus x. And then I gave you this power series for it, and it would only work between -1 and 1. And you're like, well, why in the world would you ever use the power series when you have 1 over 1 minus x? Just use 1 over 1 minus x. Well, there are certain things in the real world where there is no function that you can go use. The series, the power series is the function. And there is no function you can just go grab that's easy to work with. The power series is it. That's all you have. Okay, so here's a Bessel function. What's A?
0.
0, right? Because you don't see an x minus a number, right? You don't see an x minus a number. Okay, so part A is 0. So it's centered at the origin. So if I plug 0 into this function, right, it's going to give me a number automatically. But that's everyone knows that. All power series, easy to know that. Okay, what's the formula for C sub n? E. This one's complicated looking, right? It's everything that doesn't have the x in it. So it's -1 to the n over 2 to the 2n times n factorial squared. Whoa, that's crazy. Okay, so that's everything that did not have the x in it. And I just double checked, make sure I didn't have a typo. N starting at 0 is okay here, because if I were to plug 0 in right there for the factorial, 0 factorial is 1, so it is defined. All right, part C, I want the domain. What is the domain of the Bessel function? Well, that means you're going to have to do the limit as n goes to infinity of something here less than 1 is what we need it. Well, we want it to be this, right? We want that. All right, I'm going to give you 5 minutes to see how far you can get with trying to get this into this formula and figure out when it's less than 1. It'll be interesting to see how you handle this. 5 minutes. By the way, anytime you have an alternating series like this, -1 to the n, when you put it in here, you can just cross them out. You don't even need to worry about them because the absolute value will always kill off the -1 to any power. So you may just do that right off the bat, not even include it. It's totally up to you. I'm going to start working it out.
Professor, why aren't you including X?
I have no idea.
Oh, sorry about that. My bad.
It's not your bad. I don't know why I didn't put it there. Sorry.
I was like, oh snap, I forgot this one. What is this rule going on now? Oh.
I was doing the same thing.
Professor, when we do L'Hopital's for the limit and we have an X variable, do we still use L'Hopital's for the X variable?
You will ignore anything that has X in it because the X doesn't have an N. So you're only looking at things that have N. We're going to talk about this. Let me just clear my throat. Okay. So first thing I did was rewrote it, replacing all the n's with n+1s. So n+1 everywhere. Notice that the n+1s next to the 2's have to be in parentheses, right? And then I divide it by the original formula. I canceled the -1 to the n+1 and -1 to the n. I canceled them not because they cancel with each other, but because they're both going to turn out to be ones when we take absolute value. Is that all right? Okay, then I rewrote this. I just distributed the 2 through. So that's this. Here I distributed the 2 through. And then here, what did I do here? From here to here, I broke up the n+1 factorial as n+1 times n factorial, but both of them are still squared. Both of them are still squared. And then I rewrote the denominator, but flipped over. So any questions on that up to that point?
So can you explain again? So you put the parentheses n+1 next to the 2. How come it wasn't just like 2n+1?
Because if I asked you right now, go up to this, right? if I asked you to replace that n with n plus 1, you have to multiply it times 2, right? So there's a difference between 2n plus 1 and 2 times n plus 1. Those are not the same thing, right? Here, this top one is wrong because all you're doing is adding 1 to this. That's not what you're supposed to do. You're supposed to replace the n with n plus 1. That make sense, Ricardo?
Got it. Yeah, I was adding it. I didn't. Yeah, I wasn't replacing it. Got
Yeah,
it.
replace the n with n plus 1. So if there's a number in front being multiplied, it's going to have to distribute through. Okay, thank you for asking. All right, any other questions on how I got this from this? All right, so I'm going to keep doing this. That was just an intermediate step. I'm going to rewrite this top left corner as x to the 2n times x squared. That's this top one split up into 2 pieces. And then on the bottom, I've got, let's see, 2 to the 2n times 2 squared, splitting this up. And then this one will become n plus 1 squared times n factorial squared. So because there's multiplication here between these, I'm squaring the n plus 1 and I'm squaring the n factorial. And then the other one I'm not doing anything to. All of that was just so I could get things to cancel. We should get the x to the 2n's gone, 2 to the 2n's gone, n factorial squared's gone. Right? Limit n goes to infinity. Okay. All right. I'm just going to write the things. Let me put the thing that has x in it by itself. That right there is the only thing with x, right? That's the only thing with x. I'm going to put that in the back here, x squared. I need this to be less than 1 times. All right. Everything that did not have the x, I'm going to put it front here. So in the numerator, I took the x squared. That means the only thing I have left up top is a 1. And then on the bottom, I have a 2 squared. 2 squared is 4. And then I have an n plus 1 squared. Did I get everything? Yeah.
That's going to 0, isn't it?
Yes. Now, when we do this and we let n go to infinity, this goes to 0. Right? Times x squared, absolute value. We want that to be less than 1. Well, guess what? No matter what x you pick, if we're going to multiply it times the number that's headed to 0, this thing should be less than 1, regardless of the x you pick. Remember, you can't plug infinity in for x. It has to be a fixed number. So even if you did like a gazillion in here, it doesn't matter. This is going to 0. It's going to be small enough to kill off your gazillion squared eventually. So this should always hold, right? This will be true for all x values you could ever pick.
So we have x equals 1 variable, x equals a bound, and then we have whenever the limit equals 0, x equals all.
So if you're looking at the 3 examples I've given you, the first example, the domain of that power series was a single number. In the second example, the domain was an interval, closed on one end and open on the other. And then in the third example, the domain is what?
All real numbers.
All real numbers, everything. So that mean, right? Because we can plug in any x. So the domain of this power series is negative infinity to infinity. I've given you 3 examples with 3 different domains, right? Here's the Bessel function, just if you want to see it, there it is. Well, actually the one in red is the Bessel function graphed already, but here's my power series building it up. See, as I go further out in the series, I start to build it out, And because the domain is everything, it's going to match the picture in both directions forever.
That's really cool, actually.
Yeah. Okay.
Question,
Yeah.
because this stuff keeps making me think of it, and it's just been a minute and I don't remember for sure. There was that one function that we looked at very briefly that was basically every single point on it was a corner.
Yeah.
Was that one of these kind of things? Not a Bessel function, but a like a summation.
It is
A
a
series?
sum, but it's not a power series. It's a different type of series, but it is, you're actually referring to what was called the Wow Strauss
Yeah, that
function.
one.
And it's funny that you bring that up because I told you earlier that if you give me a function, there's a theorem that says that I can turn that into a power series, right? That's
Mhm.
called the Wow Strauss theorem. It's the same guy.
Yeah.
It's the same guy, but yeah, no, that's a different function. It's actually an infinite sum of sine and cosine functions. So it's not
Interesting.
it's not a power series. And when you do sines and cosines added up, like an infinite number of sines and cosines, you get into what are called, well, that's when you start getting into Fourier series, which engineering, you're gonna do a lot of Fourier series stuff. We don't talk about Fourier series in here, unfortunately,
Where do you talk about those?
in engineering.
Just engineering outright? Oh, okay.
I mean, but you're just gonna get shortcuts. Like you're not gonna have to analyze series. You're just gonna get like, oh, anytime you have this, here's its Fourier series. You transform it and do something with it.
Interesting.
Yeah. Okay, theorem. Big important theorem. Given a power series, right? A generic power series. There are only three possibilities when it comes to the convergence of it. First possibility is it converges only when X is A. That was our first example, right? It only converged at 0. The other possibility is that it converges for all X. That was our third example, right? It converged everywhere. Those are the best. Power series that converge everywhere are the best because there's no domain restrictions. They behave the way you want them to behave everywhere. And then the third possibility is that you actually have an interval. That's what this third thing is saying. You have an interval. That is, there is a positive number R such that the series converges if the absolute value of X minus A is less than R, and it diverges if it's bigger than that. In this last case, we call R the radius of convergence. Okay, so that last case is confusing. So what I'm going to do is illustrate this third possibility by going back up to the example we did a moment ago. Let's go look at our second example. This one right here, right? This one converged on an interval. So when we did the work and we did the ratio test, we got to this box right here. Do you all see that that looks like absolute value of X minus A is less than some capital R, some number? Do you all see that? Here, A is 3. And for us, the capital R would be 1. Y'all with me? 1. So R is 1 here. So we would say that the radius of convergence is 1. Now let me try and explain why they call it the radius of convergence. What was our interval? Our interval was everything between 2 and 4, right? So if I draw a number line, A, right? A was 3. And our radius of convergence is 1, which means if we go out in one unit in each direction, I would be at 4 and at 2, wouldn't I? And what we know is that everything between 2 and 4 works, right? That's where the name radius comes from. It's kind of like a distance from a center point. It's a distance out both ways. Now, that doesn't tell you about the endpoints. It just tells, because we determined that 2 was not included. Wait, no, 2 was included, right? 2 was included, 4 was not. But in terms of a radius, it's out a unit, 1 unit each way, and the endpoints we're not considering right now. We're just ignoring them. Everything from 3 out 1 unit without the endpoint, in the other direction 1 unit without the endpoint. I know that it converges inside there. Okay. All right, what time is it here? So there is a difference when you talk about radius of convergence, the distance you go out, right? There's kind of like 3 possibilities with the radius. Think of our first example we did. It was a single point, wasn't it? That was the only place it converged, a single point. So the radius of convergence there would be 0. Does it make sense that the radius of convergence would be 0 if you converge at a single point? Because then you can't go out in either direction. In our third example, it was all real numbers, right? Both directions forever. So we would say the radius of convergence is infinity. And then whenever you get an interval, the radius of convergence is always going to be this number, but you have to get this thing set up. When you do the ratio test, you're going to get an absolute value of x minus a less than capital R. That number R is your radius of convergence. R is just going to be some number. Okay, this talks about checking endpoints and yeah. When it comes to, when you check your endpoints, right? Let's say you're like our second example today. When you check your endpoints, there are 4 things that could happen. Either both endpoints work, both endpoints don't work, or the left endpoint works, right doesn't, or the left doesn't, right does. And so that these are the different ways that you can have it. Notice here, not including it, not including it, right? Include, 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 don't include, don't include, include. You'll see bracket, parenthesis, bracket, parenthesis. Those are the only 4 possibilities. Okay, gosh, time. I have more examples. Let's try and do one of these. Let's try and do the first one. You know what? I don't know how much time. Think that's enough time? Yeah, let's just try and crank this out. Okay, what I want to know here is I want to find the radius of convergence and I also want you to find the interval of convergence. There's a difference between the two. In this example, hopefully I'll illustrate the difference between the two. It's easier to find the radius of convergence than it is to find the interval. You'll see. So I'm just going to run right to the ratio test. Okay. So when I do the ratio test, I need the limit as n goes to infinity. Let's see, I'm going to replace everything with n plus 1, -3 to the n plus 1 times x to the n plus 1 over n plus 1 underneath the root times square root of n plus 1 over -3 to the n times x to the n. I want that to be less than 1. To save myself some time, I'm going to rewrite this as -3 to the n times -3. And then I'm going to rewrite this as x to the n times x. Y'all okay with that? Cancel some stuff. -3 to the n, -3 to the n. X to the n, x to the n. Limit n goes to infinity. All right. The only thing that has x in it is right there. So I'm going to just push that way over here to the side. And then everything that had n in it, or something else, I'm going to put here. So I have a -3 up top, I have this, and then I have this on the bottom. Those are the only other things left. So this is going to become -3 square root of n plus 1 over square root of n plus 2 times this. And I'm supposed to let n go to infinity. I'm going to get infinity over infinity, aren't I? Can you all see that? So watch what I do here. This is just a property of roots. It's easier for me to work with it like that as one root, because I can focus my attention now on what's in here, and that's infinity over infinity, but I can do L'Hopital on that, and I would just get 1, wouldn't I? I would just get 1. Okay, so this would now become, after I take the limit, this would become absolute value of -3x less than 1. And the absolute value on the 3 is going to get rid of the net, sorry, on the absolute value on the -3 will get rid of the negative. And we're almost to this point. This right here is what we're trying to get to get the radius of convergence. We're trying to get it to look like this, x minus a less than r. Unfortunately, I have a 3 in front of that x. So I'm just going to do this. This is the same as 3 times the absolute value of x less than 1, because the absolute value of 3 is 3. And then I'm going to divide both sides by 3. And now this does look like this, because that looks like x minus 0 less than 1/3. So my radius of convergence is 1/3. I've answered my first question. The next thing to do is to find the interval. So this is where I would convert this using dropping the absolute value. Right, drop the absolute value, put less than 1/3 and then greater than -1/3. And now what do you think I'm going to have to do?
Test both values.
Test both those. So I'm going to test x equals -1/3, and I'm going to test x equals 1/3. Now, I don't have time to do that. There's 2 different tests, but do y'all understand what we would have to do? Take these x values, right, and plug them into this for x. And when that happens, good things are going to happen, okay? And you're going to have to figure out what those series are, right? Imagine plugging a 1/3 right in there. You would have -3 to the n times 1/3 to the n. So you could rewrite this as -3 times 1/3 to the n, which is the same as -1 to the n. So essentially it turns into -1 to the n over square root of n plus 1. And now you've got to figure out how you're going to determine whether or not that converges or diverges. I have to leave that to you. We'll pick up in class next time.
Question.
You can go ahead and try your homework. Do as much as you can from 8.5. Yes, question?
Just real fast. Wouldn't that right there that you got there, wasn't that for the other one, the 1/3, not the -1/3?
Oh, yeah, sorry, I put that in the wrong place.
Yeah,
didn't I?
because the -1/3 should kill off your negative.
Yeah, sorry, my fault. Okay. Do what you can on the homework. Okay, 8.5. I'll come back in class next time, and I'm going to do these 2 examples. So, see what you can do.
Do our
Have a good
best.
day. We haven't had a drop of rain where I am. I don't know if y'all are getting rain. I've got
It was
nothing.
thundering and pouring on my roof all through class.
It's raining right now.
Yeah,
It's
I don't
pouring
know.
over here at the campus.
It's gonna rain all day. Nothing.
Seems like it's calmed down for me, but